Okay, hello everyone, and thank you for joining us today for this month EPSP Connect seminar. The purpose of this series is to bring the community together and also help establish connection between people you might not have been able to interact in different settings. We're very happy to have you here, and I would like to thank all of the EPSP Connect team members who help and plan organize this series, who reach out to potential speakers or panelists and coordinate with them, and who also advertise on social media and make sure that the series information is up to date on the website. Joining me today as co-host is Shashank. We will also help us with the Q&A section.
Thanks, Elvise. Hello, everyone. Thanks for joining us today. I think it's a similar exercise. If you have any questions during the talk, please put them in the chat as they come. You don't need to wait for the very end of the talk. And those of you who are joining us from YouTube live stream, we will also keep an eye for questions there as well. Over to you, Elvise.
All right, so for today's seminar, our speaker is Dr. Mirko Musa from the École Polytechnique Fédérale de Lausanne, also known as EPFL, where he leads the Sustainable River Engineering, Energy, and Morphodynamic Labs. Dr. Musa studies the interaction between renewable energy system and river morphodynamics, with a focus on sediment transport and environmentally informed hydropower design. Today, Dr. Musa will be talking about unconventional sediment training and river engineering. So please, Dr. Musa, the stage is yours.
Perfect. Awesome. Want to go ahead and share my screen. All right. Well, first of all, thank you so much. Can you? Nope, it's not the right screen. Okay, here we go. Now you can see. You should be able to see my presentation.
Yeah, we do.
Perfect. Well, first of all, hi everyone. Good morning, good afternoon, good evening, depending where you are. And first of all, thank you so much to EPSP members and the organizers for inviting me to give this talk. I'm really happy to be here. As I said, my name is Mirko Musa. I'm a fairly new assistant professor at EPFL. I started about a year ago. And here I lead the Stream Lab. As you can see, it's misspelled on purpose because it stands for Sustainable River Engineering, Energy, and Morphodynamics. I acknowledge that it's a mouthful title, but it really encapsulates well the what we do in my group, because we work with the renewable energy from water, specifically hydropower and hydrokinetic energy, but we try to do it in a way. That works synergistically with river engineering and river morphodynamics and river management. And this is essentially the leitmotif of my talk today. The theme of today's talk is to try to show you some unconventional ways to do sediment transport, to do sediment training, and to manage sediment training. Why? Well, humanity has been trying to manage river for centuries, as you all know. We mostly did it for human development, for our own gain, to gain land, to try to allow for navigation, but also to protect ourselves from flooding and so on. And how we did that? Well, we simply try to fix rivers in place. We stabilize riverbanks, straighten the course of rivers, and so resulting in basically in the suppress of their natural dynamism. We also know that, unfortunately, now we know that by doing that, we were actually harming the river system. There was this fantastic paper by Professor Jim Best in 2019 in Nature Geoscience, where he reviewed several of the anthropogenic stresses that are currently changing and in some cases degrading rivers faster than the nature can adapt to. And of course, in addition to human management, now we also have climate change that is obviously complicating things, it's exacerbating the problem. And it's also reminding us that, well, first of all, our assumption of stationarity in our hydrological statistics that we did in the past is no longer valid. But it's also reminding us that we need to come up with strategies, management strategies that are not only sustainable, but have to be also flexible and adaptable. So one way we started to addressing these problems is, of course, stream restoration. We've been increasingly adopting measures to renaturalize rivers, sometimes with mixed success, obviously. Sometimes we tried, for example, to impose an engineered quote unquote natural looking shape of the river, like a meandering shape. Moving tons of soil and with very costly interventions, and again with mixed success, or simply sometimes we just started to remove the constraints, remove the lateral constraints of the river, and let the river rewander again. Of course, this is a great solution, but obviously it's not always applicable, right? Because at the same time, we still have a lot of population centers, a lot of development, a lot of infrastructure that are still within and along the shores of big rivers. So in these cases, in these settings, of course, river management is still remain a critical necessity. And so to me, there is a need to do both of these things. So of course, restoration and protection at the same time. And we need to try to address them both in a sustainable way. And so, reflecting on my past research, I wondered, what if we can achieve both of these aspects using renewable energy technology? I know it sounds crazy, but the reason why I'm saying this is because in my past research, I did my PhD at the University of Minnesota at St. Anthony Falls Lab, so known as SAFL, and then I got a position at Oak Ridge National Lab. In my previous work, I observed that if we place hydrokinetic turbines in rivers, they actively interact with sediment dynamics, both locally and non-locally. So today I'll meander, pun intended, meander through past and more recent research to try to show you these unconventional ways to interact with sediments and trying to manage sediments, and maybe and perhaps trying to convince you that we may be able to synergistically integrate river-based renewable technology and sediment management strategies. Now, by saying this, I put this image here because this is for the early career students out there. This is how I felt during my PhD, since I was doing this mixed research. This is how I felt sometimes when I was talking about turbines to a morphological audience, and at the same time talking about meandering and morphodynamics to turbine people. So it's always been a struggle to fit in both shoes. But anyway, so today I'll try to show you some examples of first how turbines and also porous veins can steer sediments, and then how, on the other hand, multiple turbines can actually influence the morphodynamics at non-locally, so at larger scales. So, but let's start with the local influence. So this whole thing started because at the very beginning of my PhD, my project focused on looking at the interaction and the impacts of hydrokinetic turbines on the physical environment of rivers. Hydrokinetic turbines are basically essentially the same thing as wind turbines, but in water. As you can tell, the geometry is exactly the same. The working mechanism is the same. A flow, in this case, water flows through a rotor that spins the rotor and create energy. And the power that you can extract from it is proportional to the size of your device, but most importantly to the velocity of the flow, because it's to the cube. And so the first thing that we did was to look at the scour that an operating turbine could induce on the seafloor or the river floor, the rotable bathymetry. So this is, for example, a movie of the evolution of a scour downstream of a large-scale turbine model. And so we characterize both the spatial extent and the magnitude of the local scour and deposition induced by an operating turbine using a small model on an erodible bathymetry and in clear water, so without sediment transfer, but at the threshold of motion. And then we extended that study to now live bed, so with sediment transport and moving bed forms through the channel. This time here we were scanning the evolution, with monitoring the evolution of the bed by scanning the topography with sonar back and forth the channel across the turbine location. You can see the resulting movie of the dunes traveling through the turbines. And then in order to evaluate the overall impact, we average all the signal in time to evaluate the mean bed, which is this black line here. And you see that even with sediment transport, the turbine did a localized scour downstream of it. But then the mean bed recover not locally, so farther downstream, recovers to a baseline case, which is the dashed red line here, which is a case without turbine, meaning that potentially the impact, even with live bed, even with sediment transport, may be only localized close to the turbine. So through our experiment, we observed that the local scour and deposition pattern produced by a turbine was very symmetric with respect to the turbine location, and it was essentially very similar qualitatively to the more common, the more known bridge pier scour signature, right? But quantitatively, as you can tell here by this plot, quantitatively, it was much more enhanced, because now, of course, the turbine is introducing much more chaos and turbulence within the scour region. And so the flow there is much more complex. But also, as opposed to a static bridge pier scour, a hydrokinetic turbine can actually yaw. Yaw means is the yaw angle is the misalignment between the axis of a turbine and the direction of the flow. And so we wanted to test this because we had an hypothesis. We had a feeling that by yawing the direction of the rotor, you would have actually an impact on the direction of the scour and deposition pattern. And so potentially you could affect the mobility of sediments locally. And so we designed a bunch of experiments to test that, to test the effect of yaw angles. But also because since we thought that the turbine could have an impact on the directionality of sediment, we also wanted to evaluate, we were curious whether we could use this strategy at the sidewall, so placing the turbine close to the side bank, to the sidewall of the channel, as a form of erosion mitigation technique, because like the turbine is extracting energy of the flow, slowing down the velocity of the flow, so potentially slowing down the side bank erosion, while at the same time, if we were able to see this redirection of the sediment, moving sediments toward the bank itself. And so we designed, we ran several tests. First with the turbine in the middle of the channel at different yaw angle, again on the same erodible bathymetry, and again in clear water conditions, so with no sediment transport, but at the threshold of motion. We first characterized the baseline, so just a normal. We basically redid the same experiment as before with a turbine unyawed in the middle, characterized the local scour and deposition, and then we track the time evolution of the scour, and we check until it reached the equilibrium, which was reached about 2 hours into the experiment. And at that point, when the final topography was in equilibrium, we started measuring the flow behind the turbine using moving an acoustic Doppler velocimeter across the channel, so in the span-wise direction at different X location downstream, in order to characterize the wake of the turbine. The wake is essentially the region behind the turbine where the flow slows down because the turbine is extracting energy from the flow, and so you have a region of what's called the wake deficit. So the wake deficit is the difference between the incoming undisturbed flow upstream of the turbine and the flow measured behind it. And so you can, as you can see from our measurements, so all these lines are span-wise profile of the wake deficit. As you can tell, the closer you are, so the red, the warm colors are closer to the turbine. The closer you are, the bigger this wake deficit is. I acknowledge that the choice of colors is pretty poor because it's essentially the opposite as the numerical simulation. But essentially, the red colors, the warm colors, are the maximum wake deficit, which means lower velocity deficit, lower velocities, which corresponds to the blue colors here in the numerical simulation. But then you see that as you move far from the turbine, so if you move towards more downstream, the wake deficit start decreasing because now you have high momentum fluid from the side starting entraining the wake, and so starting to recover to the undisturbed condition. And so if we now stitch together all this profile that we took downstream of the turbine, you obtain the nice contour plot of our wake that it was going to be important later. So to visualize the effects of the yaw angle on both the local scour and the position pattern and the flow behind the wake, we basically plotted here the profile at 6 rudder diameter downstream of the turbine, superimposed to the final bathymetry, and then we started yawing more and more the turbine, and you see that the more negative yaw, or in other words, looking at the plot, the more the rudder starts tilting upwards, you see that both the wake and the pattern of maximum scouring deposition start also moving in that direction, start being steered toward the same direction as where the yaw is happening. And of course, the same thing is true, but in opposite, if we look at the other yaw, to positive yaw angles, you see that the rudder is tilting down, and so also the wake and the resulting pattern starts tilting and getting steered in the same direction. So now the next step was to look at if this all findings could hold when the turbine is close to the sidewall, because again, we wanted to see whether the turbine could act as could act as a stream bank protection, could either mitigate or even or in opposite enhance the side bank erosion. Because again, the idea here was to potentially use the turbine as a protector of the bank, because by extracting energy from the flow, you would shield the bank with using the wake, but at the same time steering the wake away. So you would shield the bank with the flow deficit, but at the same time you wanted to steer the wake away from the bank. You didn't want the wake to impinge on the side bank, because the wake itself is turbulent. And at the same time trying to move the sediment deposition towards the bank to act as a bank toe protector or a bank toe reinforcement. And so to do that, we basically tested 3 cases: the un-yaw at the turbine at the wall with the un-yaw condition, the negative 20 yaw and positive 20 yaw. And you see that you start seeing from both if you look at the wake and if you look how the scour deposition pattern behave and react, maybe the 20-degree, the positive 20-degree was actually doing what we're trying to do. You see that the wake is steered toward the center of the channel as opposed to the negative 20 where it's actually pushing against the channel. And at the same time is moving the centroid of the big volume, the positive volume towards the wall. You see that the centroid is getting closer as opposed to the negative 20. So we thought that maybe the 20-degree yaw was actually doing exactly what we're trying to do, and may do the trick. And so based on this result is where I got my first idea of what I'm working right now. It's to try again to try to, like, because we saw this positive feedback of by yawing the turbine, we could potentially reach that goal of protecting the bank. So what if we try to use more turbines as a stream bank protection strategy? For example, rearranging them to look like a vein. So pushing away the main flow away from the bank and protecting the bank using their collective weight. Or in extreme case, potentially putting turbines on the outside of a river meander. You know that, like, on the outside of a meander, that's where the flow is accelerated. So potentially that's where the hydrokinetic potential would be maximum, but it's also where the erosion is maximized because of, again, the fast flow and the secondary circulation that erodes sediments, and actually it's what caused meander to move. So what if we put turbines in there and we start extracting energy and maybe potentially counteract this erosion process? So this is one of the things that I'm thinking and I'm working on. But of course, there are other more classic ways to train sediment, to affect sediment motion. One of which is submerged vein. And of course, this is not a new technology, it's not a new design. In fact, it was introduced in the 80s by Professor Jakob Oetker in Iowa. As a matter of fact, these veins are also known as the Iowa veins. But we recently tested them. We recently tested a similar concept because we were trying to move sediments as a part of a larger project on reservoir sedimentation. This is when I was at Oak Ridge, and it was a collaboration between Oak Ridge, the University of Minnesota, and the Department of Energy, where we're trying to find a solution and mitigations for the issue of reservoir sedimentation. Specifically, one solution is bypassing sediment around the dam, so from upstream to downstream around the dam. Typically, it's done with the few examples in the world is done with channels, or as the University of Minnesota was proposing, trying to use hydrosuction. So hydrosuction is a technique where you would suck the sediment from upstream the dam and then siphon it around the dam. So as part of this project, we also wanted to, in order to maximize the extraction, we wanted to try to maximize to redirect as much sediments as possible towards this suction point. And so we start testing submerged veins for that reason. But as we were designing the experiments, we realized that we really didn't have a good way to measure this lateral movement of the sediment. So we didn't have a good way to quantify the efficacy of these veins. And so through our experiment, we actually came up with a new methodology to try to estimate the lateral sediment flux. And we did that from starting from high-resolution scans of bed forms. So you see here, we basically tested an array of porous vein in the main channel at Sappho, at San Antonio Falls, in live bed conditions, so with bed forms traveling along the channel. And here we were scanning 3 regions in the channel using this submerged laser scanning device that was developed at Sappho. And with that, we were actually able to identify each individual bed form on a streamwise transect at consecutive time. And using an algorithm that was developed by Jiong Lee, one of our collaborators, we extracted the geometric characteristic of each individual bed form and their migration velocity. And then using the Simon et al. Equation from 1965, we could estimate the streamwise sediment transport flux, which is calculated basically relating the geometry of single bed forms to their velocity. And so in this way, we had like sort of a Lagrangian view, if you will, of sediment transport, each dunes transporting, contributing to a little bit of sediment flux. But then we switched this Lagrangian view to a more Eulerian observation approach by conditionally averaging all the bed form characteristic, geometric characteristic, and the associated bed load transport on a regular grid for the entire domain. So by averaging all these quantities in time, so in this way we could obtain an average bed load transport rate that was spatially distributed over a 2D XY plane. And this is how we would look like. You see, these are value of streamwise bed load transport in the 3 scanned region. Of course, for a baseline case, it's fairly homogeneous, as it should be. Whereas for the vein array experiment, you see a big reduction of sediment transport capacity within the array. And that's it's easy to understand why, because the bed forms are slowing down the flow, are slowing down the bed form movement. And so they're reducing the capacity of sediment transport, the capacity of to transport sediments. And this is clear, is more evident if you take, for example, a transect within the array at x equal 3 meter, which is this panel here, the second panel here. I don't know if you see my mouse, but it would be the second panel in the lower plots. And you can see that this is the span-wise profile of the bed load flux, where the red line is the vein from the vein array. And you see that there's definitely a reduction in sediment transport within the array, in the Y values within the array, as compared to the baseline case, which is the black dashed line. But an increase in sediment transport is, you can find an increase of sediment transport in the unobstructed side, so next to the array. And that's because by continuity, the flow there is instead accelerating. So the bed forms probably are going faster, and so you have a much larger sediment transport capacity. But then downstream of the array, you see that all the bed flow, the sediment transport capacity goes back to be homogeneous like the baseline, meaning that this effect is only localized in the vicinity of the array. But this imbalance in the sediment flux that we are noticing close to the array is exactly what we think that will explain the existence of a lateral flux in the lateral direction on average. And this is even more justified, is like you can see it if you look at the instantaneous movement of sediments. If you stare at this video for as long as I did, you will start seeing that behind each vein, at some point, you will see the formation of this chevron shape that is tilted towards the left-hand side of the channel, or in this plot, towards the upper side of the plot. And you see some snapshot here in the bottom. And if you look, you will notice that the bathrooms are physically distorted and steered towards the upper hand side. And this is one of the components of this lateral transport that I'm talking about. So thanks to this Eulerian average mapping, we were now able to estimate this lateral bed load transport by simply applying mass conservation, because we're observing this imbalance in the streamwise flux. So what we did is we divided the channel into two halves, into two control volumes. One control volume is over the array, and the other control volume over the unobstructed side. And because the influx of both the control volumes is essentially the same, and it's because, as you can tell by this plot here to the left, the influx is homogeneous across the channel, then the difference between the outflux, the difference in the outflux from the two control volume, is what basically reveal the lateral, how much the sediments are displaced laterally. So this QSY is the lateral flux through the interface between the two control volumes. So if you take the difference between the two mass conservation in the two control volumes, you can get QSY, small QS, which is the lateral flux per unit length. And then, of course, if you multiply this lateral flux times the length of this interface, L, you get the total amount of sediments moved in that lateral. You get an estimation of the total mass, the total sediment flux in the lateral direction. And then by expanding this control volume, so literally moving the downstream boundary of the control volume and extending the length of this interface, we could show the longitudinal evolution of the lateral flux as you move downstream. Then, of course, because we have these gaps between the measured region, we had to introduce a corrective coefficient in order to ensure global mass balance. But essentially, these are our results. You see, the black and gray bars are this lateral flux that we quantified. The black columns are the black bars are from the vein array, whereas the gray bars are from the baseline. And of course, for the baseline, you see that there's almost no lateral flux, as it should be, whereas for the vein array, you have a pretty significant lateral flux, at least as compared to the baseline. And again, this top plot is the little QS, so the little QSY, which is the lateral flux per unit length. But then if you multiply that by the length of the interface between the two control volume, you can quantify, you can estimate the total mass that you're moving. And you see that this total mass, it's peaking around 2.5 meters, so around the third row of the array, meaning that if we were to place an hydrosuction point, here would be the best place where you would collect most of the sediment, which was ultimately the goal of our project. But we believe that this was the first attempt to quantify it, or to come up with a quantification of a lateral flux, of lateral sediment transport that we've done. So now switching gears, so far I showed you that we use turbines and porous vein to steer sediments towards a preferred direction and influence the local morphology. But now, switching gears, I want to show you how actually a pack, an array of turbines would actually affect the morphodynamic node locally, so further away from the region of influence. If you remember, earlier I showed you that one single turbine in live bed, even in live bed, would create a local scour, but I said that probably no locally, there was no much of an effect. However, that case was a very simplified, very specific case with one single turbine centrally installed in the cross section. But in real life, we actually might want to install turbines on the one side of a river, of a channel, either to try to use it as a stream bank protection, but more pragmatically speaking, to, for example, allow for navigability on the other side, or to lower installation and maintenance costs, and so on. However, this asymmetric installation could be tricky because we know from morphodynamic theories that asymmetric flow disturbances could lead to morphodynamic instabilities that are known as force bar. River bars are mesoscale forms that are characterized by region of alternating deposition and scour, as you can tell from these aerial pictures. They can be free, they can be like a natural instability arising naturally in the river, but most of the cases can be forced. They can be forced by external stressors, like in this case could be the turbines. And to me, this were the more interesting one because, first of all, they are most common in nature, they are the most observed in nature, and they are steady in space and time. And because they are steady, they are believed to be the onset, the trigger of river meandering because they impose a specific motion of the flow. And so in the perspective of evaluating the impacts of turbines in rivers, this was a big deal. So it was something that we needed to look into. So we designed this experiment where we placed two turbines on the one side of the channel, obstructing half of the channel width, running the experiments using the same hydraulic and sediment transport condition as the single turbine case that I showed you earlier. And this time, though, we were monitoring the bed evolution on two sidelines, one across the turbine, the red line, and one across the unobstructed side, the blue dashed line. And then again, we ran the experiments for a long time, and we averaged all the sonar signal in time and to evaluate the average bathymetry. And you see that the average, the mean bed from the two sideline now present an intriguing and a complex profile characterized by this steady alternating scour and deposition pattern that totally resemble the longitudinal profile of force bar, with an amplitude that was up to 18% the water depth, which is pretty significant. So because we saw this, so because we observed this phenomenon with two turbines, and because in real life, actually, in order to produce enough energy, you will have to place multiple turbines, so an array of turbines, we wanted to test the same, we wanted to try to observe the same phenomenon using a model of turbines, a model of turbine array, and perhaps try to minimize it. So we installed 12 of these little models on one side of the main channel, this time only obstructing a fifth of the channel width. And here we were monitoring the evolution of the bidimensional bathymetry using the same laser scanning device that I showed you earlier in two characteristic regions, one across the turbines and one across the unobstructed side in time. And you see here, this is the result of the scanning of the scan. You see the bed forms traveling through the array and through the unobstructed side. The gray area is the whole channel. Of course, it's very speed up. This is not the real velocity of bed forms. But then we ran this experiment for about 12 hours. We collected the data and then we averaged again to evaluate the overall effect. And you see now that from the 2D average bathymetry, you see that there are a multitude of scale of effects. You see small effects, which are represented by the classic signature behind each turbine. But then you have these patches of scour and deposition that are as big as almost as big as the array itself. So at a larger scale, so an effect at a bigger scale. So in order to evaluate that one, we essentially we filtered this average bathymetry with a low pass Fourier filter, which revealed to show this this large scale oscillation, and it revealed this longitudinal profile. If you take two lines from the two regions, you see this profile, this longitudinal profile that totally resemble the same profile that we observed with the two turbines, which is again similar to the profile of a force bar, but this time with an amplitude, an oscillation amplitude that was only 7% the water depth. And so because we observed this, we wanted to investigate this aspect more in depth. But as you can imagine, experimentally, it's very complicated because of the variety of parameters. So we turned to Professor Marco Redolfi, who's an expert in morphodynamic theories and specifically in analytical modeling. And we try to tackle this problem from a modeling perspective, and specifically to try to answer to these two very questions. So first of all, is what we're observing in the bathymetry actually on average a bar type phenomenon? And if so, how do the characteristics of the external forcing affect the resulting morphodynamics? And so we developed a fairly simple model based on the classic formulation of morphodynamic instabilities, but this time introducing the forcing as a drag force in the equation. And then we implemented that into the conventional linear perturbation approach, assuming that this drag force was small as compared to the flow momentum, so that we could neglect non-linear, higher order non-linear term and linearize the equation in the drag force. And then we essentially split the domain into two channels, an upstream channel, a downstream channel, where we found the solution as superimposition of 2D Fourier modes, which is the standard way, is exactly as has been done in the past, for example, from Soleil and Serinara 2001, and then matching the solution at the interface of the two channels where the forcing was. And this is, if you will, the novelty of our methodology, because while three of the internal boundary conditions are pretty standard, so water continuity, sediment continuity, and the conservation of transfer momentum, so no drag force in Y. The fourth one was the new part. Because now we have discontinuity in the flow, we have to assume that in erodible bathymetries, there will be a formation of a bottom step, of a bottom elevation difference. And we showed that by applying momentum balance, we demonstrated that the elevation of this step, of this form step, would be proportional to the intensity of the forcing itself. So this is really the extension, the real extension of the morphodynamic inference framework to the introduction of the forcing as a function of its own geometrical characteristic and drag properties. And so we developed new experiments in order to validate this model, using this time again a force grid as the perturbation, because the grid would introduce a very similar hydrodynamic effect in the flow as the turbines, but without the limitation of the depth, so that we could explore more water depth, and so more width to depth ratio parameters, so the beta parameters, which is very important in morphodynamics. And so we ran a series of tests. Today I'll show only two of those as a validation. These two experiments were essentially were very similar condition, same grid, very similar transport capacity, but with two different beta, and most importantly, two different proximity of beta to the beta resonant, with the GD2 being closer to the resonant value of the width evaporation. And so by comparing the model, which is the thick line, to our experiments, which is the dashed lines, you see that the model is performing pretty well. Again, these two experiments are essentially the same, except for the second having a beta number, a width to depth ratio closer to the resonant value. And that's actually why the model performed better for the second case. But overall, we're pretty happy with the model. You see that the amplitude of the morphodynamic response and the wavelength are pretty well captured in both cases. The only thing that is underestimated is the inverse distortion downstream of the switch point for GD1 probably because of the low value of beta. And so this is starting to show the limitation of a 2D model. But then we further validated also comparing the water surface elevation and the cross-sectional profile of the streamwise velocity. And in both cases, the model prediction matched pretty well the measurements from the experiments. And so we were pretty happy. And so we decided to, once the model was validated, we decided to run a series of sensitivity analysis in order to evaluate how different parameters would affect the morphodynamic response. But today I'll just briefly show the one associated to the forcing itself, because at the end of the day, that's what started this whole analytical modeling in the first place. So here you see the contour plot of the model bed elevation for the second experiments. Note that the grid extend precisely to half the channel width. And with this and this configuration creates a morphodynamic response that is perfectly anti-symmetric. Now, if we wanted to look at the effect of the intensity of the drag force, we can plot the amplitude from the first bar, the maximum part of the cross-section where the maximum force bar occurs downstream of the grid. And you see that the amplitude of this of the first force bar linearly increases with the drag force, which is expected. But then the effect of the obstruction width theta itself reveals something much more complex and interesting. When the grid is not at exactly a half channel width, but it's somewhere in between, you see that different lines here in this plot are different theta, different delta, and different delta are different varying obstruction width. And you see that as at the very near the grid, so at x equal 1, the structure of the first bar is much more complex now, because the solution is composition is composed by even and odd Fourier modes. But this rich spectral composition is only local, because the Fourier modes that are greater than the fundamental, greater than 1, spatially decay. So as we move downstream away from the grid at a location, let's say at x equal 15, you see that the result becomes again symmetric in sinusoid, because at that point only the first mode has survived. And that's also shown by this other plot, where we are plotting the bed elevation change as we increase the obstruction width. And you see that near the grid, so the blue line, so in location near the grid, the maximum effect, so the maximum scour and the maximum deposition, occurs when the grid is either at 40%, 60% or 40% respectively. But then again, further away, the maximum scour and the maximum deposition, it goes back to be maximum when the grid is halfway through the channel. But if the grid was to extend to the whole channel, then the effect would basically nullify, would vanish. And so taken all together, these results shows that the ability of the extraction to generate force power depends not on the total amount, but rather on the degree of asymmetry of the drag force. And so this also kind of suggests that, contrarily to what we thought, the nature of the forcing might have a pragmatic effect on the morphodynamic response. And so that gave me the new idea, the other idea that I'm trying to work on now is that perhaps if I'm able to manipulate even dynamically the property of the drag of this forcing, maybe I can create some more interesting morphodynamic response that are also like we can create a desired morphodynamic response. And again, perhaps we can do it using hydrokinetic turbines. So that is essentially where my ongoing work is going. That's the direction that we're taking. So keep exploring this unconventional method, but in two opposite directions. On the one hand, exploring the local influence as a form of protection, so placing turbines in a meandering channel to try to do exactly what I showed you before, like trying to protect the bank by extracting and while producing energy. And on the other hand, exploiting this non-local influence as a form of restoration. So trying to control river instabilities to trigger a desired morphodynamic response. All this towards following the same philosophy, essentially, trying to integrate both river engineering and renewable production and renewable energy production towards a shared benefit that could increase the sustainability of both aspects. So with that, I conclude my talk and I'm open to any question.
All right. Thank you very much for the nice talk, Mirko. We do have some time for questions, so I would like to quickly open the Q&A session. As a reminder, feel free to write your question in the chat. Shashank and I we will keep an eye on them. Shashank, I see we have some questions popping up already, maybe.
Yeah, Luis, thank you once again, Mirko, for the nice talk. There's a question by
Thank you, guys.
Mohammad Chaudhary. He's saying, I believe the main challenge for hydrokinetic turbines they face is in their application, is it their interaction with ship navigation. What type of river system do you think such turbine would be optimal to implement? And do we have also a flow discharge dependence on the scale of bed disturbance and the efficiency of the turbines? There are two parts of questions.
Okay, I'll start with the first one. That's a very, very good question, and that's obviously a concern. As a matter of fact, for example, the only one of the example I know of deployment of this technology that happened recently, they deployed a tri-frame of these turbines in the East River in New York, so between the Manhattan and the Queen, as a test bed. And they place it on the one side of the channel because the East River is a navigation channel. And so there was no solution around it. Like they could only dedicate a part of the channel, in that case, a part of the channel to energy extraction and the other part of the channel to navigation. There was no way around it. Now, in this technology is essentially developed mostly for tidal channels. So, like for example, the tidal channel between Europe and Great Britain, and in that case, you have such big water depth that maybe you could develop an array of turbines in at such depth that do not affect the navigation, but in either way, for safety reason, there's always going to be like a space dedicated to that. Of course, the deeper you place this turbine, the more the installation cost, and so then you have that. The other part of the question, can you remind me again?
Yeah, so the other part was, do we also have a flow discharge dependence on the scale of the bed disturbance that you showed and the efficiency of the turbines?
Well, yes, of course, the discharge will affect disturbance on the bed because, I mean, morphodynamically, you will see that like the morphodynamic influence is dependent to the intensity of sediment transport and the theta value, if you will. And of course, if you increase the discharge, you will increase the sediment transport, and so it will have an effect. Actually, it will have an effect by making it actually less impactant. I don't fully understand the second part of the second part. So the dependence of the discharge on the turbine efficiency, is that the question?
Yep.
I think so. Yeah.
Um, well, the performance of these turbines really depends on a variety of factors, one of which would be the Reynolds number. And so I would tend to say yes, but I'm not sure exactly in which way.
All right. Yeah, makes sense.
I do have a question myself that I would like to ask, Mirko. So I was wondering if there's a way to make this type of system somehow more flexible in terms of, deployment, and also the structure of the array you wanna have. Is there a way to make it flexible in space and time? For instance, I don't know, having downward-looking turbines that
Exactly,
float on the
exactly.
surface, or another type of turbine design. And what's the pros
Exactly.
and cons of this?
That's an excellent question, and that's something that I'm thinking of because if we want to make it flexible, especially if I want to try to make it to combine these turbines with stream bank protection, I won't be able to move it, and so by floating would be obviously one case. Of course, the floating creates another problem because you will see it; it will be emergent. Obviously, in terms of navigation, it's even worse. But it allows for, again, a more flexible deployment. It allows to move it, and potentially it's much easier to deploy, and so probably it will reduce the cost of deployment and maintenance, the installation and maintenance. Now, I know, for example, there is a company in the US that has a very modular uh, design. So that's another way to make it flexible, modularizing it so that it's easier to install and it's easier to be moved. There are a couple of examples in the US. One, it's installed in Alaska. It's from the company ORPC, for example, and they have like kind of like a barge design that can float, can go up and down. So that's one way. It's actually probably the best way because you can sink it and you can make it float. Probably the best way would be to something that is in between, that you can make it float, but then revert it and install the turbine upside down, or if you want, you can sink it and you move the turbine up in the upward direction. But modular designs would be probably the way to go.
Okay, very cool. All right, we're running a few minutes late, so in the interest of staying on time, I will now close the Q&A session, and I will again thank everyone for joining us today. And to close this seminar, I will hand it back to Shashans, who might have a final remarks before we wrap it up and say goodbye.
Thanks, Alvise. And thank you to Mirko for such an interesting talk. And to everyone who joined us today. We hope to see you next month too. And we have scheduled a talk on April 22nd. We will be hosting Dr. Eltner from TU Dresden, who will talk about image-based geosensor system for environmental modeling of dynamics processes. And as usual, we will be sharing more details about this talk via mailing lists and social media. So please keep an eye on them, and we'll see you next month.